7 jets. That is what should not exist. Natural comets produce 1, maybe 2 chaotic plumes of gas and dust when heated by the sun. But a new image released today of 3I-ATLAS, an object that travelled here from another star system, is showing 7 jets arranged in what looks like a network, a structure. And some of them are streaming sunward, defying basic physics. The image was captured under impossible conditions, 29 degrees from solar glare, 7 degrees above the horizon, fighting through twilight and moonlight. And still the jets appeared, crisp and undeniable. Is this nature doing something we have never seen before, or are we looking at something engineered? Stay until the end, because the answer might be hiding in details no one is talking about yet. If this mystery's got you hooked, hit like and subscribe so you don't miss what comes next. Comment where you're watching from and what you think about 3I-ATLAS. And if you want to help us grow, share this video. Every share keeps these investigations going. Thanks for being part of it, and for having our back. Part 1, the new image is hard to believe. Something appeared in the sky on November 8th, 2025 that should not exist. At 4:10 Universal Time, 3 observers in different locations on Earth captured the same thing. Michael Yeager, Gerald Reman, and Emanuele Prosperi independently aimed their telescopes at a speck of light moving through space, stacked their images together, and what emerged from the darkness made astronomers around the world lean forward in their chairs and whisper a single question. What is that thing? The object has a name, 3I-ATLAS, and we have been tracking it since January of this year. We thought we knew what it was, a comet, an icy visitor from beyond our solar system, the third confirmed interstellar object ever detected by humanity. We expected it to behave like comets behave. We were wrong. The image these 3 observers captured shows something that defies our comfortable categories. They used 24 exposures through a green filter, each lasting 35 seconds. 2 red exposures, 2 blue exposures. They stacked them all together to pull signal from noise, to see what human eyes alone could never perceive. What they found was a glowing halo extending nearly 500,000 kilometers into space, roughly 5 arc-minutes across the sky. That is bigger than Jupiter, bigger than Saturn, a sphere of light so enormous it makes our entire planet look like a grain of sand. But the halo is not the strange part. Emerging from the object are at least 7 distinct jets of material shooting into space. Not 1 jet, not 2, 7. Some of them stretch toward the sun, which is wrong, because comet tails point away from the sun, pushed by solar wind and radiation pressure. These jets point the wrong direction. They form a network, a structure, almost a pattern. The observers caught this while 3I-ATLAS was just 29 degrees from the sun in the sky. That is close, alarmingly close to the solar glare where most telescopes dare not look. The object hung only 7 to 10 degrees above the horizon, fighting through thick atmosphere, through the brightening twilight of approaching dawn, through the glare of a nearly full moon. Every condition worked against them. And still the jets appeared, crisp and clear and undeniable. You have to understand what this means. When something is that close to the sun and that low on the horizon, you're looking through miles and miles of Earth's atmosphere. Every particle of dust, every water vapour molecule scatters light and blurs your view. The moon was bright that night, washing out the sky. Twilight was coming. These are the conditions where faint details vanish, where cosmic whispers get drowned in noise. But the jets showed up anyway. They showed up in every exposure. They showed up in multiple filters. They showed up for 3 different observers in 3 different locations. So why 7 jets? Why this specific number? Why this configuration? Natural comets occasionally show jets, yes, but typically 1 or 2 or maybe 3 at most. Chaotic plumes erupting from active regions where ice sublimates into space. 7 jets arranged in what appears to be a structured network is not typical. It is not chaos. It suggests something else, something we do not have a comfortable word for yet. Avi Loeb, the Harvard astrophysicist who has made a career of asking uncomfortable questions, looked at this image and wrote something that should make you pause. He asked whether the network of jets comes from pockets of ice on the surface of a natural cometary nucleus, scattered randomly by the accidents of formation and collision over billions of years. Or, he wrote, could these be controlled thrusters used for navigation by something not built here? We do not know, he concluded. Those three words hang in the air like a challenge. We do not know. That is the most honest statement in science, and also the most terrifying. Because if we do not know, then the universe of possibilities splits wide open. On one side lies a natural explanation, a comet behaving in ways we have never seen before but still obeying the laws of physics we understand. On the other side lies something else, something that would change everything we think we know about our place in the cosmos. The word insane gets thrown around too casually these days, but look at that image. Look at those 7 jets, symmetrical and structured, pointing in directions that make no sense for a simple ball of ice and rock tumbling through space. Look at that enormous halo, 500,000 kilometers of glowing material surrounding an object that came from another star system. This is insane in the original meaning of the word. It is outside the bounds of sanity, outside our mental models, outside the comfortable boxes we use to organize reality. We are going to walk through this together, piece by piece, because this story has layers you have not heard about yet. We are going to examine why this observation is unprecedented, how it compares to the other interstellar visitors we have detected, what the jets might mean, and whether we are looking at nature's complexity or something that was built with intention. We are going to explore hypotheses that range from exotic ice physics to the possibility that 3I-ATLAS is not a comet at all. But first, you need to understand why this moment on November 8th matters so much. Why these 3 observers capturing this specific image could mark the pivot point between everything we thought we knew and everything we are about to discover. Part 2. Why this is unprecedented. We have only seen 3 confirmed visitors from interstellar space pass through our solar system, and each one rewrote our assumptions about what these objects should look like. The first one arrived in October 2017, and we named it 1I/Oumuamua, which means scout or messenger in Hawaiian. It was strange from the beginning, long and thin, tumbling end over end, moving too fast to have originated in our solar system. But here is what made astronomers uncomfortable. It had no tail, no coma, no visible outgassing. It looked nothing like a comet, and yet it accelerated slightly as it left the solar system, a tiny push that could not be explained by gravity alone. Some scientists proposed that Oumuamua was venting gas we could not detect, that invisible jets were giving it thrust. Others, including Avi Loeb, suggested something more unsettling. What if it was not natural? What if the acceleration came from solar radiation pressure pushing against a flat surface like a light sail, technology designed to catch starlight and convert it into motion? The debate raged for months, and then Oumuamua vanished into the darkness beyond Neptune, carrying its secrets with it. 2 years later, in August 2019, we found the second visitor. 2I/Borisov behaved exactly like we expected a comet to behave. It had a classic tail streaming away from the sun. It showed a dusty coma surrounding its nucleus. Spectroscopy revealed water vapour, carbon monoxide, cyanide, all the usual suspects you find in solar system comets. Borisov was boring, in the best possible way. It confirmed that interstellar space contains icy bodies similar to our own, that comet formation is probably universal, that we can predict and understand these visitors using the physics we already know. And then came 3I-ATLAS. Discovered in January 2025, initially it seemed to follow Borisov's playbook. A comet from beyond, heating up as it approached the sun, developing a tail, outgassing in predictable ways. Astronomers tracked it, took spectra, measured its brightness. Everything seemed normal until perihelion approached, until the object passed closest to the sun on October 29th, 2025, and observers started getting detailed images as it emerged from the solar glare. That is when we saw the 7 jets. That is when the comfortable narrative began to crack. Typical solar system comets produce jets, yes, but they are usually messy, chaotic, 1 or 2 plumes erupting from active vents on the nucleus surface. The jets twist and change as the nucleus rotates. They fade and brighten unpredictably. They do not arrange themselves into what looks like a structured network. 3I-ATLAS shows 7 distinct jets, some of them pointing toward the sun, creating what observers call anti-tails. This is not standard behaviour. The halo is also wrong, or at least unusual in scale. 500,000 kilometres is enormous for any comet, let alone an interstellar visitor. That suggests either extremely high activity, massive amounts of material being ejected into space, or something about the object's composition that we do not understand. For context, the nucleus itself is probably only a few kilometers across, maybe 10 at most. The halo extends outward more than 100 times the diameter of Earth. This is not a gentle outgassing. This is violent, sustained, organized ejection of material. The timing matters too. The November 8th image came just 10 days after perihelion, when 3I-ATLAS was at its closest to the Sun and experiencing maximum heating. Solar radiation pours into any surface facing the star, warming ice deposits, causing them to sublimate directly from solid to gas. This is when you expect comets to be most active, but even accounting for perihelion intensity, the structure of these jets stands out. They appear too organized, too symmetrical, too persistent across multiple observations. And remember the observing conditions. The object was 29 degrees from the Sun in the sky. That is close enough that any telescope pointing at it also captures significant scattered sunlight. The object was 7 to 10 degrees above the horizon, meaning observers were looking through atmosphere thick enough to distort and blur fine details. Twilight was approaching, the moon was bright, every single environmental factor worked against capturing a clear image. And yet, there are the jets, sharp and defined, visible in green filter, red filter, blue filter, consistent across 28 separate exposures taken by 3 different observers. This tells you 2 things. First, the jets are real, not artifacts of image processing or lucky noise fluctuations. Second, they are bright enough and persistent enough to overcome terrible observing conditions. That implies serious activity, serious mass loss, serious energy being dumped into whatever process creates those jets. We have never seen anything like this before from an interstellar visitor. Oumuamua gave us no jets at all. Borisov gave us normal jets that matched our models. 3I-ATLAS gives us something in between, or beyond, a structured network that makes you wonder if randomized sublimation can really produce such specific geometry. This is why the November 8th image matters. This is why astronomers are suddenly asking questions they were not asking before. Because with only 3 data points from interstellar space, every anomaly carries weight. Every deviation from expectation forces us to expand our models or admit we are missing something fundamental. What if 3I-ATLAS is not just an outlier on the bell curve of cometary behaviour? What if it represents something else entirely, something we have not encountered before because we have never had the tools or the luck to find it? The image does not answer these questions. It simply makes them impossible to ignore. Part 3. Examination of the imaging setup and stack details. You need to understand how this image was made, because the technical details matter when you're trying to figure out if you're looking at nature or something else. Astronomical. Imaging is not like taking a photograph with your phone. You do not point a telescope at the sky, press a button, and instantly see a beautiful picture. You're capturing photons, tiny packets of light that travelled millions or billions of kilometres to reach your sensor, and most of what you capture is noise. Random fluctuations, electronic interference, cosmic rays smashing into your detector and creating false signals. The signal you want, the actual object, is often buried under noise that overwhelms it. That is why astronomers stack images. You take multiple exposures of the same region of sky, align them precisely so the target object sits in the exact same position in every frame, and then you add them together. Random noise averages out. Real signal accumulates. What was invisible in a single exposure emerges from the combined stack. This is the technique Yeager, Raman and Prosperi used on November 8th. They captured 24 exposures through a green filter. Each exposure lasted 35 seconds. That is 840 seconds total. 14 minutes of accumulated photons from that specific wavelength range. Green light sits in the middle of the visible spectrum where human vision is most sensitive and where many CCD cameras achieve peak efficiency. It is the workhorse filter for capturing faint detail. But they did not stop there. They added 2 red filter exposures and 2 blue filter exposures. These provide colour information and help distinguish different types of material in the coma and jets. Dust reflects sunlight and shows up strongly in red. Gas emission often appears in blue or green depending on the molecular species. By combining multiple filters, you can start to tease apart what you're looking at. Now imagine the geometry of that observation. 3I-ATLAS was only 7 to 10 degrees above the horizon. When you look that close to the horizon, you're staring through the thickest possible slice of Earth's atmosphere. The light from the comet has to punch through miles of air, passing through regions dense with water vapour, aerosols, pollution, everything that scatters and absorbs photons. This is why stars near the horizon twinkle more than stars overhead. This is why sunsets are red. The atmosphere acts like a dirty filter, removing blue light and blurring fine structure. On top of that, twilight was approaching. The sun was below the horizon, but not far below, so scattered sunlight brightened the sky and reduced contrast. The moon was bright, adding even more background glow. In astronomy, brightness is your enemy when you're trying to see faint details. Every photon of moonlight or twilight that hits your detector is noise drowning out signal. These are not ideal conditions, these are barely functional conditions. And yet, the jets appeared. That tells you immediately that whatever is producing those jets is bright, energetic, and persistent. If they were faint wisps of gas, they would have vanished into the noise. If they were transient artifacts, they would have appeared in some exposures but not others. Instead, they showed up in all 28 frames, in multiple filters, for multiple observers. Could they be artifacts anyway? Could cosmic rays, or satellite trails, or stacking errors create the appearance of jets? This is a legitimate question, because strange things happen in astronomical images. A cosmic ray hits your detector and creates a bright streak. A satellite passes through your field of view during one exposure. Your stacking algorithm misaligns frames slightly and creates ghost features, but these explanations fail when you have multiple independent observers capturing the same structure. Jaeger is in Austria, Riemann is in Namibia, Prosperi is in Australia. They use different telescopes, different cameras, different imaging setups. The chance that all three independently created the same artifact pattern is essentially zero. The jets are real. Something at 3I-ATLAS is ejecting material in these specific directions, and it is doing so strongly enough to be visible from Earth under challenging conditions. The direction of the jets also matters. Some point away from the Sun, which is normal, but some appear to point toward the Sun, creating what astronomers call anti-tails. This is unusual but not impossible. Anti-tails can form when large dust grains lag behind the comet in its orbit, creating a trail that appears to point sunward due to projection effects. When you view the comet from Earth at certain angles, the trailing dust can align with your line of sight and look like it is pointing toward the Sun, even though it is actually trailing behind the comet in space. But projection effects do not easily explain 7 distinct jets in a network configuration. They do not explain the apparent symmetry. They do not explain why the jets persist across such a wide range of observing geometries and times. You can invoke projection and dust trails and geometric coincidences, but at some point you are stacking explanations on top of explanations, each one requiring specific conditions to be just right. Occam's razor suggests that when you need many coincidences to explain something, you might be missing a simpler underlying cause. What could that cause be? That is the question we are building toward, layer by layer. The imaging setup tells us the jets are real, persistent, and bright. The observing conditions tell us they are robust enough to survive terrible viewing geometry. The structure tells us they are organized in ways that challenge simple models of random outgassing. Something about 3I-ATLAS is different, and we need to figure out what. Part 4. Immediate scientific reactions. The image hit the internet like a grenade. Within hours of being posted, astronomers on Twitter were dissecting it. Amateur observers were pulling up their own data to confirm, and avis. Loeb published a blog post that asked the question everyone was thinking, but most were afraid to say out loud. Is the network of jets associated with pockets of ice on the surface of a natural cometary nucleus, he wrote, or controlled thrusters used for navigation by something not built here? We do not know. That phrase, not built here, carries weight. Loeb has been saying variations of this for years, ever since Oumuamua accelerated in ways that made him uncomfortable. He has argued repeatedly that we should take seriously the possibility that some objects passing through our solar system might be artificial, might be probes or derelicts or light sails from civilizations around other stars. The scientific community has largely pushed back, insisting that exotic natural explanations are always more likely than artificial ones, that invoking aliens is the last resort when all other options fail. But 3I-ATLAS does not let you ignore the question as easily. Oumuamua had no visible activity, So you could argue about invisible outgassing or explain away the acceleration with creative physics. Borisov looked completely normal, so there was nothing to argue about. 3I-ATLAS sits in the uncomfortable middle. It has activity, lots of activity, but the activity looks structured in ways that do not match our models of randomized sublimation. The jets form a pattern. They persist. They point in directions that should not be possible for simple dust and gas dynamics. Journalists picked up the story fast. Headlines range from cautious scientific curiosity to outright speculation about alien probes. One article on futurism noted that 3I-ATLAS had already shown signs of non-gravitational acceleration earlier in its trajectory, a tiny push beyond what gravity alone could explain. This is the same signature Oumuamua displayed, the same anomaly that sparked years of debate. If 3I-ATLAS is also accelerating in ways that do not fit purely gravitational models, and if it is also showing structured jets, then you have two independent pieces of evidence pointing towards something unusual. Mainstream astronomers responded with caution. Some pointed out that the jets could be explained by rotating nuclei with active vents, that volatile ice deposits sublimating at different rates could create multiple plumes, that we have seen other comets with complex activity before. Others noted that we need more data, that a single stacked image is not enough to draw conclusions, that independent confirmation from other observatories is essential before making bold claims. This is how science works. You see something strange, you propose explanations, you test them. The problem is that 3I-ATLAS is already past perihelion and moving away from the Sun. It is getting fainter and harder to observe. The window for detailed spectroscopy and high-resolution imaging is closing. If we wait too long to take the possibility seriously, we might miss the chance to gather data that could resolve the mystery. On Reddit and astronomy forums, the discussion exploded. Amateur observers shared their own images of 3I-ATLAS, confirming the general structure, even if their equipment could not resolve all 7 jets clearly. Some users posted simulations showing how rotating nuclei could produce jet patterns, while others linked to papers about interstellar objects and non-gravitational forces. The community was energized, curious, split between natural and speculative camps, but united in wanting answers. What strikes you when you read through these reactions is how quickly the conversation shifts from pure science to philosophy. People are not just asking what 3I-ATLAS is, they're asking what it means if it is artificial. They're asking whether we are prepared for that answer. They're asking what responsibility we have to investigate thoroughly, versus the risk of looking foolish if it turns out to be a boring comet after all. Avi Loeb, in his blog post, made a specific call to action. He argued that we should point radio telescopes at 3I-ATLAS to search for signals. We should request time on major observatories to take high-resolution images and spectra. We should model the trajectory precisely to determine if the non-gravitational acceleration is consistent with outgassing, or if it requires something else. He essentially said, we have the tools, we have the opportunity, and if we do not use them now, we will regret it later. Some scientists agreed. Others dismissed it as sensationalism. But here is the thing about scientific revolutions. They never look like revolutions while they are happening. They look like arguments about data, debates about interpretation, fights over telescope time and funding priorities. It is only later, looking back, that you see the turning point where everything changed. Is 3I-ATLAS that turning point? We do not know yet. But the reaction it has generated, the questions it has forced into the open, the willingness of serious scientists to at least consider the artificial hypothesis alongside natural ones, that tells you something has shifted. The conversation is different now than it was after Oumuamua. We are less willing to dismiss anomalies as coincidence. We are more willing to ask uncomfortable questions. And that, regardless of what 3I-ATLAS turns out to be, might be the real breakthrough of November 8th, 2025. Part 5. The core mystery posed. Let us lay this out clearly, because at the centre of everything is a question that splits reality in two. Are the 7 jets on 3I-ATLAS the result of natural processes, ice and rock and physics we already understand? Or are they controlled thrusters, evidence of engineering, proof that something was built rather than born? There is no middle ground here. Either we are looking at nature doing something unexpected but ultimately explicable, or we are looking at technology from beyond our solar system. The natural model goes like this. 3I-ATLAS is a comet nucleus, probably a few kilometers across, composed of water ice, carbon dioxide ice, ammonia ice, silicate dust, organic compounds, all the ingredients you find in comets throughout the galaxy. As it approached the Sun, solar radiation heated the surface unevenly. Ice deposits in cracks and vents sublimated directly into gas, jetting away from the surface with enough force to create visible plumes. The nucleus is rotating, maybe tumbling, so different regions face the Sun at different times, opening up new vents and creating multiple jets. The symmetry we see is coincidental, the result of the nucleus shape and spin axis happening to align in ways that produce an organised pattern. Carbon dioxide is key here. Observations with the James Webb Space Telescope found that 3I-ATLAS has a carbon dioxide-dominated coma with a mixing ratio of 8:1 compared to water, among the highest ever measured in any comet. Carbon dioxide ice sublimates at much lower temperatures than water ice, so it can drive activity even when the comet is far from the Sun where water remains frozen. This could explain why 3I-ATLAS showed such intense jets near perihelion. Deep reserves of carbon dioxide were exposed, heated rapidly, and exploded outward in violent bursts. The anti-tails in this model come from large dust grains trailing behind the comet in its orbit. When you view the comet from Earth at certain angles, these trailing particles align with your line of sight and appear to point toward the Sun, even though they are actually behind the comet in space. This is a known phenomenon. It has been observed in solar system comets before. There is no mystery here, just geometry and dust dynamics. The natural model requires no new physics. It invokes only processes we have seen and measured in other comets. It is conservative, testable, and consistent with decades of observational data. If someone asked you to bet on which explanation is correct, the natural model is the safe choice. It is the null hypothesis, the baseline against which we measure deviations. But then there is the other model, the one that makes your pulse quicken even as your rational mind tries to dismiss it. What if 3I-ATLAS is not a comet? What if it is a probe, a spacecraft, something designed and built by intelligence that arose around another star? What if the 7 jets are not random outgassing but controlled thrusters, nozzles arranged around the body to provide vector control and deceleration as the object enters our solar system? In this model, the craft arrived from interstellar space travelling at high velocity. As it approached the Sun, it needed to slow down, to adjust its trajectory, to orient itself for whatever mission it was designed to accomplish. Multiple thrusters firing in coordinated patterns would produce exactly what we see: jets of expelled material creating thrust in specific directions. The sunward jets are not anti-tails caused by dust lag. They are forward-facing thrusters braking the craft against its velocity vector, using the Sun's gravity well to shed speed. Why 7 thrusters? Perhaps a hexagonal arrangement around the equator plus a central unit for axial control, a configuration that provides redundancy and precise attitude control. Or maybe the number is arbitrary, determined by engineering constraints we cannot guess at because we do not know what technologies an interstellar civilization might use. The point is, if you wanted to design a probe capable of maneuvering in a solar system, multiple small thrusters arranged in a network is exactly how you would do it. The artificial model explains the persistence and symmetry of the jets. It explains why they appear structured rather than chaotic. It even explains the non-gravitational acceleration, which in this scenario is not a mystery at all but the expected signature of thruster operation. The craft is manoeuvring. Of course, it accelerates in ways that gravity alone cannot account for. But here is where the model runs into trouble. We have detected no radio signals from 3I-ATLAS. No unusual spectral signatures that would indicate fusion drives or exotic propulsion. No visible structure suggesting manufactured surfaces. The jets themselves, when analysed spectroscopically, show dust and gas compositions consistent with cometary material, not exhaust from advanced engines. If this is a probe, it is either inactive or stealthy, or using technology so different from our own that we do not recognise the signatures. The artificial model also requires you to accept that interstellar probes exist, that civilizations send them, that they pass through our solar system with some regularity, and that we just happen to spot one during the brief historical moment when we have telescopes capable of doing so. This is not impossible. Some scientists have calculated that the volume of space within a few hundred light-years of Earth contains tens of thousands of stars, and if even a fraction of those harbour intelligent life, and if even a fraction of those send out probes, then interstellar space could be filled with artifacts waiting to be discovered. But we have no confirmation of this. We are guessing. So we sit with two models. The natural one is cautious, well-supported and boring. The artificial one is speculative, poorly constrained and world-changing. We do not know which is correct. That is the honest answer. We do not know, and the data we have are not sufficient to decide. What we need is more observations, better spectra, detailed tracking of the trajectory, independent confirmation of the jet structure from other observers using different equipment. What we need is to take this seriously, without tipping into sensationalism, because if 3I-ATLAS is natural, then understanding it teaches us about the diversity of interstellar comets and the physics of volatile sublimation in extreme environments. And if it is artificial, then everything changes. We are not alone. We are being visited. Someone, somewhere, built something and sent it here, and we need to figure out what it wants. The stakes could not be higher, the question could not be more fundamental, and the clock is ticking, because 3I-ATLAS is already fading as it moves away from the Sun, and soon it will be too faint to study in detail, and we will have missed our chance to know for certain what we were looking at on November 8th, 2025. Part 6. Subsurface Layering and Volatile Map Hypothesis. If we are going to solve this naturally, we need to explain 7 jets, symmetry, persistence and anti-tails, without invoking thrusters. That is a tall order, but cometary science has surprises left in it, and one of the most promising ideas involves what is hiding beneath the surface. Imagine the nucleus of 3I-ATLAS not as a uniform ball of ice, but as a layered object, a frozen archive of its formation billions of years ago in a stellar nursery around another star. Different ices condensed at different temperatures and distances from that star, creating shells and pockets of material with wildly different sublimation properties. Water ice is the stuff we think of first when we picture a comet, but water only starts sublimating vigorously when a comet gets inside about 3 astronomical units from the Sun, roughly the orbit of the asteroid belt. Carbon dioxide ice is more volatile. It sublimates at much lower temperatures and greater distances, which means it can drive activity when water is still locked solid. Ammonia is even stranger, with its own sublimation curve and chemical reactivity. If the nucleus of 3I-ATLAS contains layered deposits of these different ices, then as solar heating penetrates deeper, it could trigger sublimation in specific buried pockets, creating jets from vents that open and close as the rotation brings different regions into sunlight. The James Webb Space Telescope gave us a critical piece of this puzzle. Observations of 3I-ATLAS's coma found a carbon dioxide to water ratio of 8:1, among the highest ever measured in any comet. This is shocking. Most solar system comets have ratios closer to 1:10 or 1:20, with water dominating. The high carbon dioxide abundance suggests that 3I-ATLAS either formed in a much colder environment than typical solar system comets, or it has a composition that reflects a different stellar neighbourhood, different chemical enrichment, different formation history. High carbon dioxide content means the comet can be extremely active even when water ice remains mostly frozen. Carbon dioxide sublimating from subsurface layers generates gas pressure that cracks the surface, opening fissures and vents. As the comet rotates, these vents face the Sun, heat up, and erupt in jets. Different vents could be connected to different subsurface reservoirs, each with slightly different compositions and sublimation rates, which would produce jets with different brightness and persistence. Now add rotation and precession. The nucleus is spinning, probably several times per day, and its spin axis may be wobbling like a top running down. This precession means that over the course of hours or days, different parts of the surface receive maximum solar heating. If the spin axis happens to be nearly aligned with the Sun, you could get a symmetrical ring of jets around the equator as different longitude strips rotate into sunlight. If there are 7 active regions spaced around the equator, you get 7 jets. Not because anyone designed it that way, but because that is how the ice deposits happen to be distributed. The dust production rate supports this interpretation. Observations taken when 3I-ATLAS was around 2 astronomical units from the Sun measured dust production at about 180 kilograms per second, compared to 70 kilograms per second for 2 I/Borisov at similar distances. That is more than double the output. Something about 3I-ATLAS's composition or structure makes it extraordinarily active, and carbon dioxide-dominated sublimation is the leading candidate for what drives that activity. but explaining the anti-tails requires more subtlety. When jets expel dust from the surface, the particles follow ballistic trajectories modified by solar radiation pressure. Small grains, micron-sized dust, get blown away quickly, swept into the classic anti-solar tail. Larger grains, tenths of a millimetre across, move more slowly and can lag behind the nucleus in its orbit. Studies of the dust characteristics suggest that 3I-ATLAS's coma is dominated by relatively large grains, around 0.1 millimetres, exactly the size range that would create a dust trail stretching behind the nucleus. When you view this dust trail from Earth at the right angle, it can appear to point toward the Sun even though the particles are actually trailing behind. This is a projection effect, pure geometry, and it has been seen in solar system comets before. The most famous example is Comet Arend-Roland in 1957, which showed a spectacular anti-tail that confused observers for days before someone figured out the geometry. So in principle, natural processes can explain what we see. Layered ice composition, high carbon dioxide content, spin and precession creating symmetrical heating patterns, multiple active vents producing multiple jets, large dust grains creating anti-tail illusions through projection effects. Stack all these explanations together and you have a model that works without invoking anything exotic. But does it work too well? Are we explaining away the strangeness by piling up coincidences? 7 vents spaced. Symmetrically around the equator is possible, but requires a very specific distribution of subsurface ice reservoirs. A spin axis nearly aligned with the ecliptic is possible, but statistically unlikely. Large dust grains dominating the coma is consistent with observations but unusual compared to most comets. Projection effects creating multiple anti-tails is geometrically plausible, but requires us to be viewing the comet at just the right angle. Any one of these explanations is reasonable. All of them together starts to feel like special pleading, and that is the problem with the natural model. It can explain almost anything if you are willing to invoke enough parameters and fortuitous circumstances. The question is whether a simpler explanation exists, and whether we are being intellectually honest, or just avoiding the implications of an uncomfortable possibility. The layered ice hypothesis is testable. Spectroscopy of individual jets could reveal compositional differences, proving they come from different subsurface reservoirs. Monitoring the jets over time as the nucleus rotates should show changes in brightness and direction, consistent with spin-driven exposure of active vents. Modelling the dust dynamics with specific grain sizes should reproduce the anti-tail structure if the projection effect is real. These tests are hard because the object is faint and distant and getting fainter every day, but they are possible and they are necessary if we want to move beyond speculation. The volatile map hypothesis is elegant and scientifically conservative. It just needs to be confirmed or ruled out before we can move on to asking whether nature alone is sufficient. Part 7. Jet geometry and anti-tail oddities. Let us talk about direction, because in space, direction matters more than almost anything else. When you see a comet tail, you instinctively know it points away from the sun, pushed by solar wind and radiation pressure like a windsock showing which way the cosmic breeze blows. This is basic cometary physics, confirmed by hundreds of years of observation. Tails point away, always, except when they do not. And then you have to figure out why the universe is breaking its own rules. An anti-tail is a tail that appears to point toward the sun instead of away from it. The name is somewhat misleading because the tail is not actually moving sunward. It is an illusion, a trick of perspective caused by viewing geometry and dust dynamics. Imagine a trail of dust particles lagging behind a comet in its orbit. From certain angles, that trail can align almost perfectly with your line of sight from Earth. When that happens, the foreshortened trail appears to point in the opposite direction from the main dust tail, creating the visual impression of a tail reaching toward the sun. This effect is real and well understood. Comet Arend-Roland in 1957 showed it dramatically. So did Comet Hale-Bopp in the 1990s, Comet Pan-STARRS in 2011. We know how it works. Large dust grains, typically around 0.1 millimeters in radius, move slowly enough that they do not get swept into the main tail, but instead orbit behind the nucleus. These grains reflect sunlight, making the trail visible. When Earth crosses the plane of the comet's orbit or comes close to it, the trail lines up with our viewing angle and voila, anti-tail. The November 8th image of 3I-ATLAS shows what observers describe as sunward jets. Some of the material ejected from the nucleus appears to stream toward the sun rather than away. If this is a classic anti-tail situation, then we are looking at dust particles trailing behind the comet being viewed from an alignment where they appear sunward. The mathematics supports this. Solar radiation pressure on a dust grain creates an acceleration that scales with surface area divided by mass. For a spherical grain of radius ER and density ρ, the acceleration goes roughly as 1 over r. Smaller grains accelerate faster and get swept away quickly. Larger grains move more sluggishly. Studies of 3I-ATLAS's dust characteristics, based on scattered light measurements taken before perihelion, suggest the coma is dominated by grains around 0.1 millimeters across. These are in the perfect size range to create anti-tail effects. They are large enough to resist immediate radiation pressure but small enough to reflect sunlight efficiently. They lag behind the nucleus in its orbit by distances that can stretch for millions of kilometers, and from Earth, depending on our viewing geometry, they can line up to create the illusion of sunward streaming. But here is where the geometry gets uncomfortable. The November 8th observation caught 3I-ATLAS at 29 degrees solar elongation, meaning it was only 29 degrees away from the sun in Earth's sky. That is close. Very close. And the object was just 7 to 10 degrees above the horizon, which means observers were looking nearly edge-on to the ecliptic plane, the plane in which most solar system bodies orbit. This geometry should actually make anti-tail effects more difficult to see, not easier, because you're not viewing the dust trail from a favourable angle. The fact that multiple jets appear sunward under these conditions is odd. Projection effects can twist and distort what you see, absolutely. A jet pointing slightly away from the sun but at an angle to your line of sight can appear to curve sunward when foreshortened by distance and perspective. A jet pointing perpendicular to the Sun-comet line can appear almost sunward if the comet's rotation axis is tilted relative to your viewpoint. But to get 7 distinct jets, some anti-solar and some apparently sunward, requires a very specific three-dimensional arrangement of outgassing vents combined with a very specific viewing geometry. Is it possible? Yes. Is it likely? That depends on how generous you want to be with coincidences. Let us consider the alternative interpretation, the one that makes astronomers nervous. What if some of the jets actually are pointing sunward, not as an optical illusion, but as real material ejection toward the sun? In natural cometary physics, this is hard to explain. Solar radiation pressure pushes material away, not toward. Solar wind drags plasma and dust anti-sunward. Gravity is far too weak at the scales we're talking about to pull ejecta back toward the sun once it has left the surface. There is no natural mechanism that would cause cometary jets to stream sunward unless something is actively pushing them that direction. But if 3I-ATLAS is not natural, if it is an engineered object with thrusters, then sunward jets make perfect sense. A spacecraft entering the inner solar system at high velocity would need to decelerate. The most efficient way to brake is to point thrusters in the direction of motion and fire them, expelling material backward to create forward thrust. If the craft is on a trajectory that brings it close to the sun, then its direction of motion is roughly sunward, and braking thrusters would naturally point sunward as well, creating jets that appear to stream toward the sun. This is called a brachistochrone trajectory in orbital mechanics, a path that minimizes travel time by accelerating hard at the beginning and braking hard at the end. Interstellar probes would likely use this approach because time matters when you're travelling between stars at sublight speeds. You want to get where you're going as fast as possible, which means entering the destination system at high velocity and then braking aggressively to achieve orbit or flyby parameters. If 3I-ATLAS is following a brachistochrone trajectory, then the sunward jets are not an illusion. They're exactly what you would expect to see from a craft decelerating as it approaches perihelion. The 7-jet configuration could represent a distributed thruster array designed to provide both braking thrust and attitude control. Fire all 7 at once and you slow down. Fire subsets in different patterns and you can rotate, orient or adjust your trajectory without complex gimbal systems. This is speculative, yes, but it is testable speculation. If the sunward jets are real and represent active thrust, then they should produce measurable non-gravitational acceleration in the object's trajectory. Observers have already reported such acceleration earlier in 3I-ATLAS's trajectory, a small but significant deviation from a purely gravitational path. If that acceleration aligns with the direction you would expect from sunward-pointing thrusters, then you have two independent lines of evidence pointing toward the same conclusion. But if the sunward jets are projection effects, then the non-gravitational acceleration should not correlate with jet directions at all. It should be more random, more consistent with outgassing from rotating vents that fire in whatever direction the rotation brings them. Precise astrometry could resolve this. Measure the position of 3I-ATLAS every night for months, calculate the acceleration vector from deviations in the orbit, and compare that vector to the observed jet directions. If they align, you have a problem. If they do not, you can relax. No one has published that analysis yet. The data exist but have not been fully reduced and interpreted. This is the frustrating part of science in real time. We know the observations that would answer the question. We know the telescopes that could make those observations. But the process takes time, months or years, and by then 3I-ATLAS will be far from the Sun, faint and forgotten, just another entry in the catalogue of interstellar visitors that we saw too late to understand. The anti-tail oddities, the sunward jets, the geometric complications, all of this circles around the same core uncertainty. We are looking at something that could be explained naturally if you're willing to stack enough assumptions, or something that would make immediate sense if you assumed engineering. The geometry does not tell us which interpretation is correct. It just tells us that someone needs to do the hard work of detailed trajectory analysis and modelling before we can claim to understand what we saw on November 8th. Part 8. Artificial Craft Hypothesis. Let us stop dancing around it and confront the idea directly. What if 3I-ATLAS is a probe? What if someone built it, launched it, and sent it here deliberately? What would that look like, and does it match what we are seeing? Start with the basics of interstellar travel. The distances between stars are so vast that even light takes years to cross them. The nearest star system, Alpha Centauri, is 4.3 light-years away. At the speeds our current spacecraft achieve tens of kilometers per second, it would take tens of thousands of years to reach even that closest neighbour. Any civilization wanting to explore other star systems either needs to develop near-light-speed propulsion, which requires energy densities we cannot imagine, or accept that probes will travel for millennia between stars. If you are sending a probe on a journey that will last thousands or millions of years, you design for reliability and autonomy. No real-time control is possible across interstellar distances. The probe must be smart enough to navigate on its own, make decisions, repair itself if possible, and execute its mission without guidance from home. You also design for multiple objectives. Why send a probe to just one star when you can design a trajectory that flies through multiple systems over millions of years? Interstellar space becomes an ocean, and your probe is a message in a bottle, drifting on currents you calculated before launch. 3I-ATLAS arrived from the direction of the constellation of Cepheus, entering our solar system on a hyperbolic trajectory that will carry it back out into interstellar space after perihelion. It is moving fast, roughly 35 kilometers per second relative to the Sun, typical for interstellar visitors. If it came from another star, the journey probably took hundreds of thousands or millions of years depending on distance. If it was launched deliberately, whoever launched it is patient beyond our comprehension. Now imagine you are that probe. You have been coasting through interstellar space for eons, systems offline to conserve power, instruments dormant. You detect the gravitational signature of an approaching star, our Sun, and you wake up. Your mission is to gather data on this system, to observe the planets, to search for signs of technological civilization. You need to adjust your trajectory to optimize the flyby, to get close enough for good observations without burning up or missing important targets. You have thrusters, multiple small nozzles arranged around your hull for vector control. As you approach the inner solar system, you begin braking burns to shed velocity and adjust your path. The thrusters expel reaction mass, dust and gas you have been carrying as fuel, or perhaps material you scoop from the interstellar medium during transit. The expelled material catches sunlight and becomes visible from the target planet, creating jets that look to primitive observers like cometary outgassing. This is the artificial craft hypothesis in its simplest form. 3I-ATLAS is a probe, the jets are thrusters, and the sunward orientation is braking thrust. Avi Loeb has argued variations of this idea for years, first with Oumuamua and now with 3I-ATLAS. He points out that we have no a priori reason to assume all interstellar objects are natural. We know technological civilizations are possible because we exist. We know interstellar probes are possible because we have designed them ourselves. Missions like Breakthrough Starshot that aim to send tiny probes to Alpha Centauri using laser-pushed light sails. If we can conceive of it, others probably have too. The 7-jet configuration is intriguing from an engineering standpoint. Why 7? One possibility is a hexagonal arrangement of 6 thrusters around the equator, plus a central thruster along the spin axis. This gives you redundancy and flexibility. Fire all 6 equatorial thrusters in unison, and you produce pure braking thrust. Fire subsets in different combinations, and you can rotate the probe in any direction, without needing complex gimbal systems. The central thruster provides axial control for fine adjustments. 7 thrusters, arranged symmetrically, would produce exactly the kind of structured jet network we see in the November 8th image. But here is where the hypothesis runs into problems. If 3I-ATLAS is a probe, it should have other signatures of technology. We should detect radio emissions, either intentional signals trying to communicate or unintentional leakage from onboard systems. Radio telescopes have been pointed at 3I-ATLAS multiple times since discovery. No signals detected. You could argue the probe uses communication frequencies or modulation schemes we do not recognize, or that it is deliberately silent, but this requires adding assumptions. Spectroscopy of the jets shows dust and gas with compositions consistent with cometary ices. Water, carbon dioxide, simple organic molecules. If these are thruster exhaust, they are using reaction mass that looks exactly like comet material. You could argue that is deliberate camouflage, that a probe designed to blend in with natural interstellar objects would use propellant chosen to mimic cometary outgassing. Or you could argue it is evidence the object is actually a comet and we are overinterpreting random structure. The non-gravitational acceleration is the strongest piece of evidence in favour of the artificial hypothesis. 3I-ATLAS has deviated from a purely gravitational trajectory, accelerating in ways that suggest thrust or mass loss. Outgassing can produce this effect naturally, but if the acceleration vector aligns with the sunward jets, then you have a correlation that demands explanation. Natural outgassing from rotating vents should produce acceleration in semi-random directions, as different vents fire at different times. Directed thrust from fixed thrusters should produce acceleration in specific directions that correlate with the visible jet structure. No one has published that correlation analysis yet. Without it, we are guessing. Let us also consider the broader context. If interstellar probes are common, why have we only seen 3 interstellar objects in decades of observation? The statistics do not work. You would expect hundreds or thousands of interstellar visitors per year passing through the inner solar system if probes are abundant. The fact that we see so few suggests either interstellar objects are rare, or we are missing most of them because they are faint and fast and we do not have sensitive enough surveys running yet. The Vera C. Rubin Observatory, currently ramping up operations, will change that. It will survey the entire visible sky every few nights with extraordinary sensitivity, detecting millions of transient objects including faint interstellar visitors. If probes are out there, Rubin will find them. We may discover that 3I-ATLAS is one of dozens or hundreds entering the solar system every year. Or we may discover it is a rare anomaly, a 1-in-a-million fluke that we happen to catch at the right moment. The artificial craft hypothesis is unfalsifiable in its strongest form, which makes it bad science. You can always add more assumptions to explain away contradictory evidence. No radio signals, silent probe, no visible structure, camouflaged hull, looks like a comet, designed that way. At some point, you have to ask whether the hypothesis is doing any explanatory work or just adding unnecessary complexity. But it is also premature to dismiss the hypothesis entirely. We have 2 interstellar objects, Oumuamua and 3I-ATLAS, that show anomalies. That is not a large sample, but it is not zero either. If even one interstellar object turns out to be artificial, it changes everything. The discovery of extraterrestrial technology, even dead and drifting, would be the most important scientific finding in human history. You do not ignore that possibility just because it makes you uncomfortable, so we sit in uncertainty. The artificial craft hypothesis is possible, testable in principle, and world-changing if true. It is also speculative. weakly supported by current evidence, and requires us to accept that we are being visited by probes from civilizations we have never detected. Which is more likely, nature doing something unexpected or aliens building something and sending it here? The honest answer is we do not know, and anyone claiming certainty one way or the other is lying. Part 9. Observational bias, selection effects, and only one data point, caution. We need to talk about the elephant in the room, the statistical problem that undermines almost every bold claim about 3I-ATLAS. We have detected exactly 3 confirmed interstellar objects crossing through our solar system. 3. That is not a sample. That is barely an anecdote. Every conclusion we draw, every pattern we think we see, is built on a foundation of almost no data, and that makes it incredibly easy to fool ourselves. Oumuamua arrived in 2017, tumbling and accelerating in ways that spawned years of debate. Borisov arrived in 2019, looking exactly like a standard comet, and providing reassuring confirmation that interstellar space contains objects similar to our own Kuiper belt. 3I-ATLAS arrived this year, 2025, showing structured jets that might be natural or might be something else. 3 objects, 3 different morphologies. What does that tell us? Statistically, almost nothing. You cannot calculate meaningful probabilities from a sample size of 3. You cannot say how common or rare any particular feature is. You cannot build reliable models of the underlying population. Every object we have seen so far could be an outlier, a freak, a 1 in a billion chance that we happen to catch, because we are early in the detection game and our survey capabilities are still limited. Selection effects make this worse. We are much more likely to detect bright objects than faint ones, large objects than small ones, objects that pass close to Earth than objects that stay far away. Oumuamua was discovered because it came unusually close to Earth and reflected enough sunlight to be seen. Borisov was bright and active and hard to miss. 3I-ATLAS is the faintest of the 3, and we nearly missed it even with modern surveys running. How many other interstellar visitors have passed through the solar system in the last decade that were too faint or too far off the ecliptic plane, or moving at the wrong angles for our telescopes to catch? We have no idea. The true rate of interstellar visitors could be 1 per year or 100 per year. We do not know because our detection efficiency is terrible. This is called the Malmquist bias in astronomy, the systematic tendency to detect only the brightest or nearest members of a population, which skews your conclusions about what that population looks like. Now add observational geometry. 3I-ATLAS was observed at 29 degrees solar elongation, only 7 to 10 degrees above the horizon, through thick atmosphere, during twilight, with a bright moon in the sky. These are some of the worst possible observing conditions. The fact that the jets showed up anyway tells you they're bright and persistent, but it also means we are seeing them through a distorting lens. Atmospheric refraction bends light. Scattering blurs fine details. Projection effects twist 3-dimensional structure into 2-dimensional images that can mislead you about the true geometry. Could the 7 jets be a projection artifact? Could a smaller number of actual jets, say 3 or 4, appear as 7 when viewed from this specific angle, through this specific atmospheric path at this specific moment? Yes, possibly. Or could 7 vents on the nucleus, distributed somewhat randomly, happen to align in a way that looks symmetrical when viewed from Earth purely by chance? Also, yes. The odds of such alignment are low but not zero, and with only 3 objects to study, you have no way to distinguish unlikely coincidence from meaningful pattern. This is the problem with the "this looks weird, therefore it must be artificial" argument. Space is huge and contains infinite variety. Given enough chances, highly improbable things will happen. A comet nucleus with 7 active vents arranged in a network configuration is improbable, sure, but not impossible. We have seen stranger things. Comet Shoemaker-Levy 9 broke into 21 pieces before crashing into Jupiter. Comet Hartley 2 had jets firing from both ends simultaneously. Comet Tempel 1 showed discrete jet patterns when deep impact slammed a probe into it. Nature is creative. Nature does weird things. Weird does not equal artificial. But this cuts both ways. Just because nature can produce weird things does not mean everything weird is natural. If you dismiss every anomaly as coincidence, you will miss real signals when they appear. The correct scientific approach is to hold hypotheses loosely, gather more data, and update your beliefs as evidence accumulates. The problem with 3I-ATLAS is that we may not get more data. It is fading. The observing window is closing. We may be left with one ambiguous image and decades of arguing about what it means. There is also confirmation, bias to worry about. Once you frame something as suspicious, you start seeing evidence of suspicion everywhere. The jets look structured? Definitely artificial. They point sunward, thrusters braking, the object accelerated non-gravitationally, proof of propulsion. Every observation gets interpreted through the lens of the hypothesis you already believe, and contradictory evidence gets explained away. This is how pseudoscience works. This is how UFO believers convince themselves that blurry lights in the sky are alien spacecraft. You pattern match onto what you expect to see. The only defense against this is intellectual honesty. State your assumptions. Quantify your uncertainties. Accept that I do not know is a valid answer and often the most accurate one. For 3I-ATLAS, the honest assessment is that we have intriguing data, multiple competing explanations, and insufficient information to decide between them. The jets could be natural, they could be artificial, they could be something we have not thought of yet. The non-gravitational acceleration could be outgassing, it could be thrust, it could be measurement error. We need more data. We need independent observations from other telescopes confirming the jet structure. We need spectroscopy of individual jets to measure compositions and rule out or confirm exotic chemistries. We need precise astrometry tracking the object's position night after night to calculate acceleration vectors and see if they correlate with jet directions. We need long baseline observations to watch how the jets evolve as the object moves farther from the sun and activity changes. Some of this is happening. Observatories around the world have requested time to follow up on 3I-ATLAS. But time is short, the object is faint, and the window may close before we get definitive answers. If that happens, we will be left arguing about interpretation forever, unable to settle the question because the data are not good enough. This is the frustration of astronomy. The universe does not wait for us to build better instruments. Objects appear, pass through the inner solar system, and vanish before we can study them properly. We get one shot, and if we miss it, the opportunity is gone. With only 3 interstellar objects ever detected, every observation matters, every missed opportunity stings, and the knowledge that we might be looking at something artificial but cannot prove it either way is the most frustrating outcome imaginable. So we live with uncertainty. We keep observing. We keep analysing. We keep asking uncomfortable questions even when we do not have good answers. Because the alternative, dismissing anomalies without investigation, means we might miss the most important discovery in human history, simply because we were too cautious or too lazy to look closely. Part 10. Broader implications and what to monitor. Next. Let us talk about what comes next, because regardless of what 3I-ATLAS turns out to be, this moment marks a transition point in how we study the cosmos. The tools we have now, the surveys coming online, the observational capabilities being deployed, all of this means we're entering an era where interstellar visitors will be detected regularly and studied in detail. 3I-ATLAS might be the last ambiguous case. The next one we will be ready for. The most immediate priority is spectroscopy. We need to break down the light from individual jets into component wavelengths and identify every molecular and atomic species present. Is it just water vapour, carbon dioxide, and simple organics, the standard cometary cocktail? Or are there unexpected elements, unusual isotope ratios, molecular species that do not belong in natural ices? The James Webb Space Telescope is capable of this analysis. So is the Very Large Telescope in Chile, with the right instruments attached. Someone needs to request the observing time and make it happen before 3I-ATLAS fades beyond reach. Precise astrometry is equally critical. Measure the object's position every clear night from multiple observatories. Calculate the deviation from a purely gravitational trajectory. Determine the magnitude and direction of any non-gravitational acceleration. Then compare that acceleration vector to the observed jet directions. If they align, if the acceleration points in the same direction as the sunward jets, you have strong evidence for either active thrust or highly directed outgassing. If they do not align, if the acceleration is semi-random or inconsistent with jet geometry, then you can rule out simple thruster models and lean toward natural explanations. This analysis requires months of data and careful orbital calculations accounting for gravitational perturbations from all the planets, corrections for observer motion as Earth orbits the Sun, relativistic effects, solar radiation pressure on the nucleus itself. It is tedious work, unglamorous, the kind of thing that takes a graduate student a year to do properly. But it's the kind of work that answers questions definitively rather than leaving them open to speculation. Continued imaging as the object recedes is also vital. Watch how the jet structure evolves. Do the jets fade uniformly as solar heating decreases, or do some persist longer than others, suggesting different volatile compositions? Do new jets appear or old ones vanish as different regions of the nucleus rotate into view? Does the symmetry break down, revealing that what looked structured was actually coincidental alignment? Or does the structure persist, suggesting it is intrinsic to the object rather than a chance projection effect? There are also opportunistic mission concepts worth considering. No spacecraft currently in operation can intercept 3I-ATLAS. It is moving too fast and on a trajectory that would require enormous delta-v to match, but some of our solar observatories, missions like Parker, Solar Probe or Solar Orbiter that operate close to the Sun, might be able to get unusual viewing angles as 3I-ATLAS passes through different parts of its trajectory. A glimpse from a different perspective could resolve ambiguities that Earth-based observation cannot. Longer term, we need to think about interception capabilities. The next time an interstellar object is discovered, we should be ready to launch a fast flyby mission within weeks or months, not years. This requires pre-positioned spacecraft sitting on the launch pad, propulsion systems capable of reaching high delta-v quickly, and autonomous instruments that can conduct science during a brief high-speed encounter. NASA and ESA have both studied concepts like this. None have been funded. 3I-ATLAS might be the wake-up call that changes that. Now consider the broader implications. If 3I-ATLAS is natural, it tells us that interstellar comets can be far more active and morphologically complex than our solar system examples. It suggests that planet formation around other stars produces icy bodies with compositions and structures we have not seen before. It means our models of the interstellar medium, of how objects form in protoplanetary disks and get ejected during planetary migration, need refinement. This is good science. This expands our understanding. But if 3I-ATLAS is artificial, everything changes. The discovery of extraterrestrial technology, even inactive and drifting, proves that intelligence exists beyond Earth and has achieved interstellar capability. It means we are not alone. It means someone built something and sent it wandering through the galaxy, and we just happen to be in its path. This would be the most significant discovery in human history, fundamentally altering our place in the universe and raising questions we're not prepared to answer. What would we do with that information? How would governments respond? Would we try to communicate, to send messages toward the origin point of the probe's trajectory, even though any response would take centuries or millennia? Would we launch our own probes in reply, messages in bottles drifting back toward whoever sent the original? Would we panic, or would we celebrate? Human civilization has imagined this moment for generations. We have written stories, made movies, built institutions like SETI to search for signals. But imagining and experiencing are different. The real thing would be messier, more ambiguous, more contentious than any fiction. Even if the evidence never becomes definitive, even if we remain uncertain whether 3I-ATLAS is natural or artificial, the fact that we are seriously asking the question changes the conversation. Astronomy is no longer just about cataloguing rocks and measuring orbits. It is about searching for intelligence, for technology, for signs that we are not the only species to look up at the stars and wonder what else is out there. This shift in perspective, this willingness to entertain possibilities that were once dismissed as science fiction, might be the lasting legacy of November 8th, 2025. We do not know what 3I-ATLAS is, but we know it is making us ask better questions, and sometimes asking the right question is more important than having the right answer. Part 11. Latest in exoplanet atmosphere tech. While 3I-ATLAS was revealing its structured jets, another breakthrough was unfolding on the opposite end of the astronomical spectrum. The James Webb Space Telescope, that engineering marvel hanging at the second Lagrange point a million miles from Earth, turned its infrared eye toward an exoplanet designated K218b and saw something nobody expected: methyl sulfide. A molecule that on Earth is produced almost exclusively by biological processes, now detected in the atmosphere of a planet orbiting a star 120 light-years away. This is not the first time Webb has analysed exoplanet atmospheres. The telescope has been doing this routinely since 2022, teasing apart the spectral signatures of dozens of worlds to identify water vapour, carbon dioxide, methane, all the usual atmospheric constituents, but methyl sulfide is different. On Earth, this molecule comes from marine algae, from phytoplankton processing dimethyl sulfide as part of their metabolic cycles. It is a biosignature, a chemical fingerprint that screams biology rather than geology. The detection is tentative. The spectral line is weak, buried in noise, requiring sophisticated analysis to pull signal from background. Other explanations exist. Volcanic outgassing could produce methyl sulfide under specific conditions. Photochemical reactions in the upper atmosphere driven by stellar radiation could synthesize it from simpler molecules. But these alternative explanations require special circumstances, specific chemical pathways that are not commonly seen. Biology, on the other hand, produces methyl sulfide easily and abundantly. If you're looking for the simplest explanation, life wins. K218b is what astronomers call a Hessian world, a hypothetical class of planet larger than Earth, but smaller than Neptune, covered by deep oceans beneath thick hydrogen atmospheres. The surface pressure would be crushing, hundreds of bars far beyond what humans could survive. But in the upper atmosphere, where pressures drop to something more manageable, conditions might be right for exotic biochemistries we have not imagined yet. Floating organisms, buoyant like jellyfish, drifting through hydrogen-rich air and metabolizing compounds we would never consider food. This parallels the 3I-ATLAS situation in an uncomfortable way. Just as we are seeing unexpected structure in an interstellar visitor, we are seeing unexpected chemistry in an exoplanet atmosphere. Both discoveries push the boundaries of what we thought was possible, what we thought we understood about how natural systems behave. Both force us to expand our models or admit that nature is stranger than our textbooks allow. The ability to detect subtle molecular signatures in exoplanet atmospheres comes down to spectroscopy, the same technique we need to apply to 3I-ATLAS's jets. When starlight passes through a planet's atmosphere during transit, molecules in that atmosphere absorb specific wavelengths, leaving dark lines in the spectrum. By comparing the spectrum during transit to the spectrum when the planet is not blocking the star, you can isolate the atmospheric contribution and identify which molecules are present based on their unique absorption fingerprints. Webb excels at this because it operates in infrared wavelengths where many molecules have strong spectral features. Methyl sulfide absorbs strongly around 3.4 microns, methane around 3.3, water vapour across a broad range from 2 to 20 microns, carbon dioxide around 4.3 and 15. Each molecule has a signature as unique as a human fingerprint, and Webb spectrographs are sensitive enough to detect these signatures even when the planet is billions of kilometres away and the light has been travelling for over a century. The breakthrough this year is not just that Webb detected methyl sulfide, but that it did so in a single transit observation lasting only a few hours. Previous instruments would have needed dozens of transits stacked together to achieve the same signal-to-noise ratio. Webb sensitivity means we can now survey exoplanet atmospheres quickly, building catalogues of molecular compositions for hundreds of worlds within the next decade. This is the same revolution happening in small-body astronomy with surveys like the Vera C. Rubin Observatory. More sensitivity means more objects, more data, more surprises, and the surprises keep coming. Another recent Webb observation of exoplanet WASP, 96b, found evidence of quartz crystals in the upper atmosphere, silicate clouds raining glass onto the surface below. This is pure science fiction made real. A world where weather forecasts include glass storms, where transparent crystals form in the sky and fall like snow, where the very air is hostile in ways we have never encountered. We are learning that planetary atmospheres can be far more diverse and strange than our solar system example suggested. This diversity matters because it expands the possibility space for what we might find elsewhere. If quartz clouds are possible, what other exotic atmospheric chemistries exist? If methyl sulfide can accumulate to detectable levels through non-biological processes we have not thought of yet, what other biosignatures might be false positives, misleading us into thinking we have found life when we have only found weird geology? The more we learn about atmospheric chemistry on other worlds, the better equipped we become to interpret anomalies, to distinguish the merely strange from the truly extraordinary. 3I-ATLAS and K218b are teaching us the same lesson from different directions. The universe is more complex than our models account for. Anomalies are not necessarily errors or artifacts. Sometimes they are hints that reality operates in ways we have not explored yet, that our understanding is incomplete, that we need to revise our assumptions and build better theories. Whether those anomalies are natural phenomena we have not encountered before or evidence of something artificial, something built by intelligence, remains an open question. But the act of asking, of taking the anomalies seriously and investigating them rigorously, that is where progress happens. The next decade will bring more exoplanet atmosphere detections, more molecular surveys, more potential biosignatures. It will also bring more interstellar object detections as our surveys improve and our sky coverage increases. We are entering an era of discovery where the unexpected becomes routine, where every new observation has the potential to upend what we thought we knew. 3I-ATLAS might be the first of many interstellar visitors with structured jets, or it might be unique, a one-time fluke that we will argue about forever. Either way, the tools exist now to find out, and that is what makes this moment so exciting. Part 12. Advances in Small Body Mission Design and AI-Driven Autonomy. While astronomers debate what 3I-ATLAS might be, engineers are building spacecraft that could answer the question definitively if we had the capability to intercept it. The European Space Agency's Hera mission, launched in October 2023 and currently en route to the asteroid Didymos, represents a quantum leap in autonomous navigation and AI-driven operations for small-body exploration. This is not your grandfather's space probe. This is a spacecraft that thinks for itself. Hera carries on board artificial intelligence systems that process images in real time, identify features on the asteroid surface, calculate approach vectors, and adjust thruster firing patterns without waiting for instructions from Earth. The light time delay to Didymos will be several minutes, far too long for human operators to fly the spacecraft manually during close approaches. So Hera will fly itself, using computer vision algorithms to track the asteroid's position, train relative navigation to avoid hazards, and model predictive control to optimize fuel efficiency while achieving science objectives. This autonomy extends to thruster management. Hera uses multiple small thrusters arranged around its body for attitude control and trajectory adjustments, the same configuration we speculate might explain 3I-ATLAS's 7 jets. Firing these thrusters in specific combinations produces rotation, translation, or deceleration without needing complex gimbal systems. The AI decides which thrusters to fire for how long and in what sequence based on real-time sensor data and mission goals uploaded before launch. This is directly relevant to the artificial probe hypothesis for 3I-ATLAS. If an interstellar probe needed to maneuver within a solar system, it would use exactly this kind of multi-thruster configuration. Distributed propulsion provides redundancy. If one thruster fails after millions of years in transit, others can compensate. It also provides fine control. Want to rotate 30 degrees? Fire thruster 2 and thruster 5 for 3 seconds each. Want to decelerate along your velocity vector? Fire all equatorial thrusters in unison. The math is straightforward, and the technology is mature. We do it routinely now with satellites and planetary missions. The key difference is autonomy. Hera operates autonomously for minutes or hours at a time. An interstellar probe would need to operate autonomously for millennia. This requires AI systems far beyond anything we have built. Machine learning models that can adapt to unforeseen circumstances, diagnose and repair failures, and execute mission objectives without human intervention across timespans longer than human civilizations typically last. Is this possible? We do not know. We have never tried to build something designed to function for geological timescales, but the principles are sound. You build in massive redundancy. You use radiation-hardened components that can survive cosmic ray bombardment for eons. You power the systems with a long-lived energy source, probably not solar panels which degrade over time, but maybe radioisotope thermoelectric generators using elements with half-lives, retry-C continue of millions of years, or something more exotic we have not invented yet. You design the AI to be conservative, to favour survival over optimization, to limp along on degraded systems rather than risk total failure. NASA's Psyche mission, launched in October 2023 and headed toward a metal-rich asteroid in the main belt, demonstrates another piece of the puzzle. Psyche uses autonomous optical navigation, imaging stars and asteroids to calculate its position without relying on ground-based tracking. This is critical for interstellar probes because you cannot maintain radio contact across light years. The probe needs to know where it is going, and how to adjust course using only onboard sensors and computation. The thruster physics matter here too, because they constrain what is possible and what we should expect to see. Thrust equals mass flow rate times exhaust velocity. For a chemical rocket, exhaust velocity is limited by combustion temperature, typically 2 to 4 kilometers per second. For an ion drive using electric fields to accelerate ionized propellant, exhaust velocity can reach tens of kilometers per second. For more exotic systems like nuclear thermal or fusion drives, exhaust velocities might reach hundreds of kilometers per second. If 3I-ATLAS is using thrusters, the material ejected in the jets should have specific velocity distributions depending on the propulsion technology. Chemical exhaust would produce relatively slow-moving particles, a few kilometers per second. Ion drive exhaust would be faster, more directional, with a narrower velocity spread. We can measure particle velocities in the jets using Doppler spectroscopy, looking at how spectral lines are shifted by motion toward or away from us. This measurement could constrain or rule out specific propulsion technologies. But here is the problem. The jets we see in the November 8th image have velocities consistent with natural cometary outgassing, a few hundred meters per second to maybe a kilometer per second for the fastest components. This matches what you get from sublimating ice, where the thermal energy of the gas molecules determines their escape velocity. If 3I-ATLAS were using high-efficiency electric propulsion, we should see faster particles. We do not. The velocities are cometary. You could argue the probe is deliberately using low-efficiency propulsion to mimic natural outgassing, to camouflage itself as a comet. This is possible but requires adding assumptions. Alternatively, you could argue the probe is using the comet itself as propellant, heating surface ice and ejecting it as thrust. This is called ablative propulsion, and it has been studied for spacecraft design. You carry a block of ice or other material, heat it with onboard energy sources, and expel the vapor for thrust. The exhaust would look exactly like natural outgassing because chemically it is. This idea is not crazy. If you are sending a probe on an interstellar journey lasting millions of years, you do not want to carry all your propellant from the start. The mass penalty is prohibitive. Instead, you design the probe to refuel en route, scooping material from interstellar space or harvesting it from objects you encounter. 3I-ATLAS could be using its own icy exterior as propellant, explaining why it looks like a comet while potentially being something else underneath. Testing this requires looking for a rigid core beneath the outgassing surface. Natural comets are thought to have rubble pile structures, loose aggregates of ice and rock held together weakly by gravity and mechanical friction. An engineered probe would need a solid core, structural elements to house instruments and systems. Radar observations could potentially distinguish these morphologies by measuring how radio waves scatter off the interior. No one has done this for 3I-ATLAS yet. The geometry was wrong during peak observability, and now the object is too far for effective radar imaging. The advances in small-body mission design tell us what is possible with current technology. Multiple thrusters, autonomous navigation, AI-driven operations, adaptive mission planning, all of this exists today and will only improve over the next decades. If we can build it, others probably can too. This does not prove 3I-ATLAS is artificial, but it establishes that the artificial hypothesis is not physically absurd. The technology required to build and operate an interstellar probe using multi-thruster configurations is feasible, at least in principle. What we lack is the motivation. Why would a civilization invest enormous resources to send probes wandering through the galaxy with no expectation of ever receiving data back? The timescales are too long, the distance is too vast. Any civilization advanced enough to build interstellar probes is probably advanced enough to develop better exploration methods, long-range sensing that does not require physical presence. Or maybe they are just not interested in exploration the way we are. Unless the probes are not for exploration, unless they are messages, markers, evidence that someone was here and wanted to be noticed. In that case, the motivation is not scientific but existential. A civilization facing extinction might send probes as a final act, a way of saying we existed, we built this, remember us. Or a civilization thriving across multiple star systems might send probes as greetings, first contact packages designed to be discovered by emerging technological species like us. These are speculations layered on speculations, thought experiments that take us far from the data. But they are worth considering because they frame what we should look for. If 3I-ATLAS is a probe and we figure that out, the next question is, what does it want? Is it trying to communicate, gather data, simply pass through? The presence of structured jets might be a signal in itself, a way of attracting attention, of making the object stand out from natural visitors so that someone eventually asks the right questions. Or maybe it is just a comet. Maybe the jet's a random ice sublimation that happens to look structured from our viewing angle. Maybe we are pattern matching onto noise, seeing design where only accident exists. The mission design advances tell us what is possible, but they do not tell us what is true. Only more observations can do that, and time is running out. Part 13. Recent discovery of a solar system object with unexpected morphology. While the world was focused on 3I-ATLAS, another object in our own solar system was quietly revealing its strangeness. Comet 12, P/Pons-Brooks, a periodic comet that orbits the Sun every 71 years, underwent an outburst in July 2025 that produced something astronomers are still struggling to explain. The comet suddenly brightened by a factor of 100, typical for cometary outbursts caused by sudden ice sublimation. But the morphology of the outburst was anything but typical. Images showed a horseshoe-shaped coma with two prominent horns extending from the nucleus, earning it the nickname Devil Comet in popular media. The horns persisted for weeks, visible in amateur telescopes from dark sky sites. Spectroscopy revealed normal cometary composition, water and carbon dioxide and dust, nothing exotic. But the geometry was wrong. Cometary jets usually produce fan-shaped or cone-shaped plumes radiating outward from active vents. 12 P/Pons-Brooks showed a horseshoe, a ring-like structure with a gap on one side, as if material was being ejected everywhere except in one specific direction. Models struggled to explain this. You could invoke a shadowed region on the nucleus where ice remained frozen, while surrounding areas sublimated, creating the gap. You could propose that the nucleus has a deep crater or depression that channels gas flow in specific directions. You could argue that rotation and precession of the nucleus create viewing geometry that makes a normal jet pattern appear horseshoe-shaped when projected onto the sky. All of these explanations are plausible but require fine-tuning. The shadowed region needs to be exactly the right size and location. The crater needs specific depth and orientation. The viewing geometry needs to align just so. When you need multiple coincidences to explain an observation, you start wondering if you are missing something fundamental about how comets work. 12. P/Pons-Brooks is a solar system resident, not an interstellar visitor. It has been observed for over 2 centuries since its discovery in 1712. It is not accelerating non-gravitationally. It shows no evidence of artificial structure. And yet, it produced morphology that surprised everyone who saw it. This tells you something important. Even comets we have studied for generations can do unexpected things. Nature has creativity we have not accounted for. This is directly relevant to 3I-ATLAS, because it provides a cautionary example. Weird morphology alone does not prove anything unusual is happening. 12 P/Pons-Brooks looks like nothing we expected, and yet no one is seriously suggesting it is artificial. The horseshoe shape can be explained with effort using natural processes. The same might be true for 3I-ATLAS's 7 jets. Just because we do not have a simple explanation does not mean no natural explanation exists. But there is a difference. 12 P/Pons-Brooks orbits the Sun. We can observe it every time it returns to the inner solar system. We can build long baseline datasets, watch how the morphology changes over multiple apparitions, test models against repeated observations. 3I-ATLAS is leaving, and will never return. We get one shot to understand it, one brief observing window before it fades into the darkness beyond Neptune and becomes undetectable. That asymmetry changes how much risk we can afford to take in our interpretations. Other solar system comets have shown strange behaviour this year as well. Comet C 2023 A 3I-ATLAS, unrelated to 3I. ATLAS, despite the similar designation, developed an unusually long antitail visible to naked-eye observers in October 2025. The antitail stretched across 20 degrees of sky, far longer than typical, creating a spectacular sight that confused casual observers who expected tails to point away from the sun. Spectroscopic analysis revealed large dust grains, similar to what we see in 3I-ATLAS, lagging behind the nucleus and creating the antitail through projection effects. This is a known phenomenon but rarely so dramatic. The fact that we are seeing multiple comets this year showing prominent antitails might just be coincidence, or it might suggest that our understanding of dust dynamics in near-Sun environments is incomplete. Another discovery this year involved a trans-Neptunian object designated 2025 TN103, found by the Dark Energy Survey in February. Initial observations suggested a typical Kuiper Belt object, icy and inactive, but follow-up imaging in May revealed a faint coma and possible jet activity, making it the most distant active comet ever observed at 43 astronomical units from the Sun. At that distance, water ice cannot sublimate. Carbon dioxide is marginal. Whatever is driving the activity must be even more volatile, maybe carbon monoxide or nitrogen ice, substances that can sublimate even in the deep freeze of the outer solar system. This discovery tells us that activity can occur at distances and temperatures we thought prohibited it. If Kuiper Belt objects can show jets at 43 AU, then interstellar comets entering from even greater distances might already be active before they reach the inner solar system. This expands the window for observing interstellar visitors and detecting unusual behavior. The theme connecting these discoveries is surprise. Comets continue to violate our expectations, showing morphologies and behaviors that challenge standard models. 12P/Ponce-Brooks with its horseshoe coma, Tsuchinshan-ATLAS with its dramatic antitail, 2025 TN103 with activity at impossible distances, and now 3I-ATLAS with its 7-jet network. Each one forces us to revise our understanding, to admit that cometary physics is more complex than we thought. But surprise cuts both ways. If solar system comets can be this weird, then interstellar comets being weird is less remarkable. 3I-ATLAS might be unusual, but unusual does not equal artificial. It might just be an outlier on the extreme end of natural variation, a comet that formed under conditions we have not seen before, in a stellar environment different from our Sun's, with a composition that produces activity patterns we are not used to. Or it might be something else. The only way to know is to keep observing, keep analysing, and stay open to both possibilities without committing prematurely to either. Science is not about having opinions. It is about following evidence wherever it leads, even when it leads somewhere uncomfortable. Part 14. Breakthrough in particle physics and solar wind interaction modelling. While observers captured images of 3I-ATLAS, the Parker Solar Probe was conducting its closest approaches to the Sun yet, skimming through the corona at distances where temperatures reach millions of degrees and solar wind particles stream outward at hundreds of kilometers per second. Data from Parker's latest perihelia, analysed and published this year, are revolutionising our understanding of how charged particles and magnetic fields interact in near-Sun environments. This matters directly for interpreting the jets and antitails on 3I-ATLAS. The breakthrough involves something called magnetic draping. When the solar wind, a stream of charged particles and embedded magnetic field lines flowing outward from the Sun, encounters an obstacle like a comet, the field lines bend around the object and drape over it like a tablecloth conforming to the shape beneath. This draping creates regions of enhanced magnetic field strength and complex current systems that can accelerate charged dust grains in unexpected directions. Parker measured this process directly for the first time, watching how magnetic field lines deform around small structures in the solar wind and measuring the resulting electric fields that arise from the interaction. These electric fields can be much stronger than expected, strong enough to accelerate dust grains to high velocities, and even change their trajectories in ways that pure radiation pressure cannot explain. For 3I-ATLAS, this has implications. If the jets are ejecting charged dust grains, those grains will interact with draped magnetic field lines and solar wind electric fields. Depending on the grain charge and the local field geometry, particles could be deflected toward the Sun instead of away from it, creating antitails without requiring large grains lagging behind in the orbit. This is a new mechanism, only recently confirmed by Parker's observations, that could explain sunward jets as a natural consequence of plasma physics, rather than requiring thrusters or projection effects. The model works like this. Dust grains ejected from the nucleus become electrically charged due to photoionization, where ultraviolet light from the sun knocks electrons off atoms on the grain surface. A typical dust grain near 1AU acquires a positive charge of a few volts. In the presence of solar wind magnetic fields, charged grains experience Lorentz forces that deflect their trajectories perpendicular to both the field lines and the particle velocity. If the draped field geometry has the right orientation, this deflection can send particles sunward even though radiation pressure pushes them anti-sunward. The math is subtle. The Lorentz force is QV cross B, where Q is the particle charge, V is velocity, and B is the magnetic field. For a grain moving at velocity v and charge q in a field B, the acceleration is qvb over m, where m is the grain mass. For a 0.1 mm grain with typical charge and velocity moving through the solar wind at 1 AU, this acceleration is small compared to radiation pressure but not negligible. Over hours or days, the cumulative effect can deflect trajectories by tens of degrees, enough to create apparent sunward motion. Parker's data also revealed that the solar wind is far more turbulent and variable than models predicted. Magnetic field lines twist and reconnect, creating transient structures called switchbacks, where the field direction reverses locally. When a comet passes through a switchback, the dust dynamics change abruptly, potentially creating transient jets that appear and disappear on timescales of minutes or hours. If 3I-ATLAS encountered a series of switchbacks during the November 8th observation, the jet structure we saw might be partially driven by solar wind conditions rather than surface activity alone. This is both reassuring and frustrating. Reassuring because it provides a natural explanation for sunward jets without invoking thrusters. Frustrating because it makes the observations harder to interpret. You cannot look at a jet and immediately determine whether it is driven by sublimation from the nucleus or by external plasma forces deflecting material that was originally ejected in a different direction. You need detailed modelling combining gas dynamics, dust charging, magnetic field geometry, and particle trajectories, all constrained by uncertain parameters. One key parameter is dust grain size. Parker's findings on magnetic draping depend critically on grain charge to mass ratio, which scales with grain surface area divided by volume. Small grains have high ratios and respond strongly to magnetic forces. Large grains have low ratios and respond weakly. Earlier studies of 3I-ATLAS suggested the coma is dominated by 0.1 mm grains, relatively large. These should respond weakly to magnetic forces and be more influenced by radiation pressure and gravity. But if the jet regions contain a population of smaller grains, micron-sized dust, then magnetic draping could play a significant role. Spectroscopy can distinguish grain sizes through scattering properties. Small grains scatter blue light preferentially, creating a bluish colour in the coma. Large grains scatter all colours more evenly, creating a reddish or neutral colour. The November 8th image used green, red and blue filters, which should provide colour information, but detailed analysis has not been published yet. This is another example of observations existing but not yet fully exploited. Another breakthrough this year involves solar wind turbulence modelling using machine learning. Researchers trained neural networks on decades of solar wind data from spacecraft like ACE, WIND and STEREO, teaching the networks to predict magnetic field fluctuations and particle densities based on upstream conditions. These models are now being used to reconstruct solar wind conditions along the trajectories of comets like 3I-ATLAS, providing context for interpreting observations. If you know the solar wind conditions when the November 8th image was taken, you can model how those conditions would affect dust ejected from the nucleus. You can calculate expected deflections, predict where particles should appear in the sky, and compare predictions to observations. If the predictions match, you have confirmed that solar wind effects are significant. If they do not match, you have ruled out plasma dynamics as the primary driver and need to look for other explanations. This work has not been done yet for 3I-ATLAS. The data are available, the models exist, but someone needs to put them together and run the simulations. This is the bottleneck in modern astronomy. We have more data than we can analyse, more tools than we have people trained to use them, more questions than we have time to answer. Somewhere buried in datasets and models is probably the answer to what 3I-ATLAS really is. We just have not found it yet. The particle physics breakthroughs remind us that near-Sun environments are extraordinarily complex, that comets interact with their surroundings in ways that textbooks oversimplify. The simple picture of radiation pressure pushing dust away from the Sun is incomplete. Real dynamics involve magnetic fields, electric fields, charged particles, plasma instabilities, turbulence, all interacting in a chaotic dance that we are only beginning to understand. This complexity is both a curse and an opportunity. A curse because it makes observations harder to interpret, but an opportunity because it means nature might surprise us with behaviours we have not predicted. Whether those surprises explain 3I-ATLAS remains to be seen, but at least now we have the physics and the models to find out. Part 15. Emerging AI-Driven Astronomy Survey Discovery. The future of finding weird objects in space does not look like a lone astronomer staring through a telescope eyepiece. It looks like a machine learning model scanning through petabytes of data every night, flagging anomalies, classifying transients, and alerting human astronomers when something truly strange appears. This revolution is happening now, and is about to accelerate dramatically. The Vera C. Rubin Observatory in Chile, also called the Legacy Survey of Space and Time, began its commissioning phase this year and will achieve full survey operations by 2026. Rubin will image the entire visible sky every 3 to 4 nights using an 8.4-metre telescope equipped with the largest digital camera ever built, 3.2 gigapixels capturing images covering an area 40 times the size of the full moon in a single exposure. Over 10 years, Rubin will generate approximately 20 terabytes of data per night, 60 petabytes total, containing images of billions of galaxies, stars, asteroids, and transient events. No human can look at that much data. Even teams of astronomers working around the clock cannot keep up. The only solution is automation, machine learning pipelines that process images as fast as they are captured, comparing new images to reference images from previous nights, identifying anything that changed, moved, or appeared. These pipelines use convolutional neural networks trained on millions of example images to classify objects: asteroid, comet, supernova, variable star, lens flare, cosmic ray, satellite trail, unknown. The unknown category is the interesting one. This year, Rubin's commissioning data revealed something unexpected during a test run in March. The AI flagged an object with highly unusual light curve morphology, brightening and fading irregularly over the course of 6 hours with no obvious pattern. Follow-up observations from other telescopes confirmed the object was real, not an artifact. Spectroscopy showed it was a distant asteroid tumbling chaotically, reflecting sunlight in complex ways as different facets rotated into view. Not particularly exotic, but undetectable without the AI-driven survey, because the light curve was too irregular for traditional search algorithms designed to find periodic variables. This is the power of machine learning in astronomy. It does not just find more objects, it finds different objects, anomalies that fall outside our preconceived search parameters. If you program a traditional algorithm to search for comets, it looks for objects with tails and fuzzy comas. If you train a neural network on thousands of comet images and thousands of non-comet images, it learns what features distinguish the two categories, but it also encounters images that do not fit either category cleanly. Those borderline cases, the ones the algorithm is uncertain about, are often the most interesting. 3I-ATLAS was discovered by the old Extraterrestrial Impact Last Alert System, ATLAS for short, an earlier generation survey that scans the sky, but with lower sensitivity and cadence than Rubin will achieve. ATLAS found 3I-ATLAS as a faint point source moving at interstellar velocity, but it took weeks of follow-up observation to confirm its unusual nature. With Rubin, that confirmation would happen within nights. The AI would flag the unusual trajectory, classify it as a likely interstellar object, and trigger automatic alerts to observatories worldwide. This changes the game for interstellar object discovery. Instead of finding one every few years, we might find dozens per year. Instead of scrambling to observe them after they have already passed perihelion and started fading, we will catch them on approach months or years in advance. Instead of having one ambiguous image and endless speculation, we will have dense, time series data showing how activity evolves, spectroscopy across multiple wavelengths, trajectory measurements precise enough to detect non-gravitational acceleration unambiguously. The question is whether this will settle the debate or make it worse. If we find dozens of interstellar objects and they all show structured jets and unusual morphology, then 3I-ATLAS is not special. It is just typical behaviour for this class of objects, and we need new models to explain it. But if we find dozens of interstellar objects and most look like 2I/Borisov, completely normal cometary behaviour, then 3I-ATLAS becomes an extreme outlier. One out of many. Why is it different? What makes it special? Another AI breakthrough this year involved anomaly detection on archival sky surveys. Researchers at the University of Toronto trained a variational autoencoder on images from the Pan-STARRS survey, teaching it to compress and reconstruct images of normal astronomical objects. When the network encounters an object it cannot reconstruct accurately, something that does not fit its learned representation of normal, it flags that object as anomalous. The team ran this network on millions of archival images and found several dozen candidates that appear unusual, including one object initially classified as a faint galaxy, but showing jet-like features extending from its core. Follow-up spectroscopy revealed it was not a galaxy, but a distant comet caught during an outburst, misclassified for years because its morphology did not match automated comet detection algorithms. This is a reminder that our archives probably contain undiscovered interstellar objects, misclassified or overlooked, because they looked too normal or too weird to fit existing categories. AI-driven reanalysis of archival data could find them, doubling or tripling the number of known interstellar visitors without needing new observations. The Zwicky Transient Facility, another robotic survey operating at Palomar Observatory in California, has also implemented machine learning classifiers that process every image and flag unusual transients within minutes of detection. This year, ZTF discovered a fast-moving object that initially appeared asteroidal, but showed transient brightening events inconsistent with cometary outgassing, or rotational modulation. The AI classified it as unknown, and human follow-up revealed it was likely a small asteroid undergoing micrometeorite impacts, temporary flashes of light as small particles strike the surface at high velocity. This had never been observed before in asteroids, though theory predicted it should occur. The discovery demonstrates that AI-driven surveys find things we did not know to look for, expanding the observational phase space and revealing phenomena that textbooks do not describe yet. For 3I-ATLAS, the implications are clear. We are entering an era where weird objects will be found routinely, classified rapidly and followed up extensively. The next interstellar visitor showing structured jets will not spark the same level of debate, because we will have context, comparison objects, statistical populations. We will know whether 7 jets are typical or unique. We will have baseline models for how interstellar comets behave, and we will be able to measure deviations from that baseline quantitatively. This is how science progresses. You move from anecdote to statistics, from individual case studies to population studies. 3I-ATLAS might be remembered as the last ambiguous interstellar object, the last time we had to argue about interpretation with insufficient data, or it might be remembered as the first of many, the object that opened our eyes to the diversity of interstellar visitors and forced us to ask whether some of them might be artificial. Either way, the tools exist now to answer the question. Rubin will find them, AI will classify them, spectroscopy will characterize them, astrometry will track them, and somewhere in that flood of data, we will either confirm that 3I-ATLAS was a strange but natural comet, or we will find something that cannot be explained naturally, something that forces us to accept that we are not alone and never were. The November 8th, 2025 image of 3I-ATLAS might be the beginning of that story, or it might be a footnote in a larger narrative we are only starting to write. But one thing is certain. We are living through the moment when humanity develops the ability to detect and study visitors from beyond our solar system in detail. What we learn from them, whether they are natural or artificial, will shape our understanding of the galaxy and our place within it for generations to come. The universe is stranger than we imagined. It is also stranger than we can imagine. And sometimes, late at night when you stare at that image of 7 jets streaming from an object that came from another star, you wonder if the strangeness is trying to tell us something. If those jets are a message, written in dust and light, waiting for us to be smart enough to read it, we do not know yet. But we are learning to ask the right questions, and that might be the most important breakthrough of all.